this video, we are going to talk about Thévenin equivalence. I am Fatima from the EC department of the University of Utah. Have you ever faced these complicated circuits with lots of independent sources and resistors, and you wondered if there is any way that you can simplify this circuit before adding other stuff to it? The good news is that in a lot of cases, yes, you can, and Thévenin will help us with that. Thévenin theory basically says that in a linear circuit, no matter how many resistors you have, no matter how many independent sources you have, you can treat the whole circuit like a black box and replace it with one single voltage source in series with a resistor that we call it Thévenin resistor. So now the question in here is how to find Thévenin voltage and how to find Thévenin resistance in a complicated circuit. So let's start with the easiest one, the Thévenin voltage. By looking closely at the circuit, you see at port A and B, the voltage should be the same as V Thévenin. Because this is an open circuit, therefore there is no current flowing through it. So there is no voltage compensated at R Thévenin. So basically, V Thévenin should be the same as the voltage across port A and B when it is open and nothing else is connected. So you can just simply hook up a voltmeter at port A and B and measure the V Thévenin in your circuit. Alright, so now let's see how to find R Thévenin in a circuit. As you can see in this simple schematic in here, for finding R Thévenin, if we turn off V Thévenin, basically we can just measure R Thévenin by hooking an ohm meter across port A and B. So for turning off V Thévenin, we need to turn off all the independent sources in the circuit. You leave the dependent sources on though. For turning off all the independent sources, you need to replace independent voltage sources with a wire and replace current sources, independent current sources, with an open circuit. Okay, after you do that, then you can easily find what R Thévenin is by measuring it. There are other various ways that you can find Thévenin resistance, but in here we don't include them. Let's show this with a practical example. At the left side of the circuit, you see a 5 volts power supply connected to a 20k ohm and a 30k ohm, and we are going to show you how to find the Thévenin voltage and how to find Thévenin resistor at the left side of that circuit. So the LED there indicates that when the power supply is involved in the circuit, the LED turns on. After we find Thévenin equivalent circuit, then we add loads such as 24k ohm and 12k ohm to see if the response of the circuit, original circuit at these loads, is the same as the Thévenin equivalent circuit. This is the picture of the board that we made it ready for you and built it. So now let's start the measurements. So this is the breadboard and the circuit that we built for the Thévenin. And we have a few switches over in here that every time we want a component get involved in the circuit, we just turn it on. We first start with a very simple circuit to just have one 5 volts voltage source in series with a 20k ohm, and we are going to measure the V Thévenin and R Thévenin for this simple circuit. For this, let's actually turn on the 5 volts, and for providing these 5 volts power supplies, we just used USB phone chargers that are 5 volts. It was pretty convenient to do that. Okay, if we measure the voltage across port A and B in here, that we connected it to a voltmeter in the background that is connected via Bluetooth to this iPod, we get around 5 volts, which is pretty close to what we are expecting to get. So now let's measure the R Thévenin in this circuit. For that, we need to turn off the power supply, which in here, we just turn it off, and when it is turned off, let's just substitute with a wire. And then we measure the resistance to be 19.98, which is pretty close to 20. And that's what we are expecting to get as our RThevenin in this simple circuit. Okay, so now let's be bold a little bit and make our circuit a little bit more complicated. In here, we add another 30 k ohm resistor in series to 20 k ohm. And let's measure now what would be the VThevenin here. We are expecting this to be 3/5 of the total voltage, because if you use a voltage divider in here, 30 over 20 plus 30 is just a 3/5 of the total voltage. So we expect our VThevenin to be around 3 volts. Okay, let's see if we really get 3 volts when we turn on the power supply and when we have our 30 k ohm resistor involved in the circuit. Let's turn it on. Pretty close, 3 volts. So now our VThevenin is 3 volts. Now let's measure RThevenin by turning off the power supply and replacing it with a wire that this switch does it automatically. And measure the resistance. Basically, in the digital multimeter, we just switch from voltage to ohm or resistance, and we get 12. And that is what we expect to get, right? Because if you look at this schematic, it's a 30k in parallel with a 20k. And if you calculate the two parallel resistors equivalence, you get 12k, which is what we expect. Okay, now this shows in the circuit that we just showed you with a 5 volts power supply, a 20k and a 30k, the Thévenin equivalent circuit consists of a 3 volt voltage source in series with a 12k ohm resistor. Now let's add to the port A and B, let's put some loads in here and see if the original circuit measurements does agree with what we are going to calculate in the schematic that has the Thévenin equivalence in it. For this start, let's just put a wire across A and B. You're expecting to get 0 volts, right? Let's see if we really get that. If we put this wire over here and here, we get 0 volts. That's good. That's a good start. Okay, so now let's make it a little bit more complicated by turning this 12k ohm and get it involved in the circuit. So now this is a schematic of our circuit. Okay, by looking at this schematic, if we want to find the voltage across 12k, it's just going to be half of the voltage because you have two 12k's in here, so you're expecting half of the voltage of the power supply be across 12k. So we are expecting it to be 1.5 volts. Interestingly, the measurements across port A and B, as you see in the original circuit, the measured voltage is also close to 1.5 volts. So the original circuit is exactly behaving the same as the Thévenin equivalent here. Let's change the resistor here, and instead of the 12k, we get the 24k involved in the circuit. So now we have a 24k ohm load in series with the 12k. We are expecting 2/3 of the power supply voltage be contributed across this 24k ohm, which is 2 volts. Interestingly, the voltage measured across ports A and B is 2 volts, which is the same as we calculated for the Thévenin equivalent circuit. And it's a good news. It means that you can simplify your circuit in the future. Thank you.